good morning from here in London. Welcome to today's Siemens Global webinar. Today's topic we'll be looking at empowering machine builders for virtual factory acceptance tests. I'm delighted to welcome as your speakers today, Mr. Scott Felber and Mr. Colm Gavin. Their bios are up on the screen. I'll just touch on a few things as we do have a very packed morning. Scott is an NX product engineering software marketing manager here with us at Siemens. His main task is to help customers and prospects identify value around the use of our products and tools with a main focus on NX for design and how that integrates into their processes. He can also discuss the use of NX in the context of Team Center, across process automation and other upstream and downstream uses of the design data. He works with customers and prospects every day to help them build and plan to transform their businesses and processes. He has over 25 years of experience with us here at Siemens. A very warm welcome to Scott. Following up from Scott, we have Colm, who's Portfolio Development Manager and has worked for Siemens for 19 years and is currently responsible for the promotion of digitalization topics from the software group for machine and line builders. Within this role, he has leveraged his extensive experience in discrete manufacturing to help companies take advantage of new innovations from Industry 4.0. So very warm welcome to Colm. Without further ado, Scott, let me unmute you. I've just passed you over the ball.
All right, thank you, Jay. Good afternoon, good evening, and good morning, everybody. Welcome to today's session. We're going to talk about how, as machine builders, you can use virtual factory acceptance testing now to kind of move your business forward. So really, as machine builders, what we're really seeing is that most machine builders have really up to four essential requirements that their manufacturers or the people they're building their machines for really are the key things that you need to overcome to embrace virtual factory acceptance testing. And I'm going to go through each one of these requirements that machine builders are given from their customers in a little more detail here coming up. The first one is reduce setup time. And what really are some of the requirements and challenges around reduced setup time? The first one is, how can I validate my machine sequence and throughput early on in my cycle while it's still in the digital phase? And the last one, really starting to hit home now, is that we can see how can I reduce these travel costs to do actual on-site factory acceptance testing at the machine builder. Because with today's limited travel and other conditions around the world, we're seeing that to be a real problem. How do we get out into, and not only that, how do we get there? How do we get into our customers' factories at this point in time with social distancing and everything else? So how can I do more and more of the work digitally to get up to speed? The next one is flexible product handling. And this really encompasses two big things, right? The first one is the ability in today's world to manufacture different products on one machine as we move more and more towards personalization of products. So what we need to do is, how can we really validate that we can go ahead and produce all of the variation that our machines are needed by not having to go ahead and physically produce all those machines? We want to virtually validate all of that. And the last one is, how can we handle retrofits to existing machines that we've already built or installed out in our customer base to be able to change them for new product designs? How can we virtually prove these out, all while reducing time that we shut down how our customers shut down their lines, so we can go ahead and do that? The next one, of course, is quality. Quality is important everywhere. And really, there's two ends of quality on this one. The first one is the quality of the parts those machines produce. The second one is, how can we as a machine builder increase our value to our customers? And what we mean by that is, how can we set up guaranteed uptime for those the manufacturers that need our machines? How can we have predictive maintenance schedules and monitoring back to guarantee their uptime? And finally is one for operator training. How can we install a new machine into a plant? How can we validate that all the workers will be able to use those machines right away, day one, without having to take a lot of time, again, out on the shop floor and have them trained up on how the machines work, what all the screens mean, and how the interfaces all work to those machines? So really, to really overcome a lot of these requirements, what you need to do is start adopting a virtual factory acceptance test to get through these four items as quick as possible. But really, how does that really affect you, and where does this start as being a machine builder? Really, to begin to do virtual factory acceptance testing, you need to embrace the comprehensive digital twin. And what we can see here is we can see a virtual machine that we have running in Mechatronics Concept Designer. We'll talk a little bit about this more in detail later, showing it moving through its steps. And this is really where the digital twin starts, is with the design of the machine. But not only the design of the machine, it's really the automation of the machine. And really here, when we start talking about the comprehensive digital twin, what we see here is we have on the left-hand side, we have the virtual machine. And on the right-hand side, we have the virtual digital twin of the controller. So what we want to do is virtually bring up the machine and the automation groups together. So as we move into production, all we need to do is go ahead now and build that machine and then transfer that automation routine into the physical controller, and then everything works. So we can quickly and easily get up to speed and make sure our machine will work for all the conditions we want it. And really, this digital twin technology is being adopted across all the industries that Siemens supports across the globe. Some are leading the way a little bit more, and if you're in some of these industries, you'll see those now with some of the boxes. For instance, automotive and robotics are really requiring their machine builders to give them digital twins of not only their machines, but maybe the entire cell and the plant layout. And in a little bit, Colin will talk about not only what we're here to talk about today, which is single machines, but the entire portfolio that Siemens brings to help machine builders get everything set up. The tire and electronics industries, too, are very big in digital twin. Food and beverage, interlogistics, aerospace, of course, machine building and cranes. And these are some of the ones that are leading the way. Now, this isn't covering all the industries, and you may be in some of these other industries. If you're in some of these other industries that today do not have a box around them, it's really good to start embracing digital technology, because that'll give you a competitive advantage and a lead against some of your competitors if you operate in some of these industries across the globe. But really, all of this digital twin and virtual factory acceptance testing, what does this really lead to? Well, what does it all have in common? It really, on your end, you're thinking now, this really leads to what we call the explosion of complexity. And some people say the answer is to try to limit or manage complexity. But we at Siemens really believe that true disruptors won't be those trying to limit complexity. We believe that if businesses want to move faster, if they want to lower their cost of development and production, all will be able to quickly respond to changing customer demands and out-innovate their competition and become industry leaders. We believe these companies will need to embrace complexity as a competitive advantage. So really, in a complex world, some argue that with enough data, the numbers speak for themselves. What this implies is the end to the scientific and science methods. But sometimes we have seen that studies of data have just shown that there are correlations due just to the sheer size of the data and not really the nature of that data. So in other words, too much information tends to behave like very little information. For example, there's a very high correlation between the number of people in the United States of America that have achieved a doctorate degree in civil engineering and the per capita consumption of mozzarella cheese. So is there really a correlation between cheese and degrees? We don't think so. So sometimes you still have to go back and look at what's really going on with the data. And we really accomplish this through our three key components in our strategy. The most comprehensive digital twin, which is what we're going to talk about quite a bit today. Also, we have a very personalized, adaptable, and modern infrastructure to be able to adapt to all the areas you need to address. And the last one we talked earlier about is when we get into virtual factory acceptance testing, not only can you do this only with a Siemens ecosystem of products, we also are very open that you can bring your own products in. And we'll talk about that in a little bit later with Calm about what products outside of Siemens you can connect into this virtual factory acceptance testing methodology. So really, but data is not the end of itself. You must analyze the data and get the business essence out of it. And here is where really Internet of Things and IIoT comes back with, which in our area is Mindsphere. So Mindsphere is our open cloud-based IoT operating system that allows us to aggregate and analyze and transform the data into actionable information that can be reported back to both product development and product planning. And what this allows you to do is now create a closed-loop environment for continuous decision-making and optimization. That will allow you now to create the ideal delivery to get ideal products out into the market. And this holistic approach, we believe, is where Siemens leads the industry in all of these areas together. So we saw how we went in that last one, virtual production, virtual product to virtual production, to real production, into real products. So really what we're going to focus on today is really that second bubble in there, and most of ours is going to be in that virtual production. How do we tie the virtual products, which include the machines, the automation, the software, everything else we need, and get it into real production? And that's really what we want to call it with virtual production. And with virtual production, we can set up virtual production, virtual factory acceptance testing to get that out to the end users. And how really does this digital twin validate the machine behavior for manufacturers? And this is a slide we'll come back to later, but what you can see here is kind of the same thing we were talking about. On the left-hand side, we have the virtual machine, and on the right-hand side, we have the virtual automation or the sensor list here from TIA Portal. And what we do is we tie these two together. So behind the scenes, through time, you tie the two together, and then what you have is the actual automation reading the virtual sensors and their conditions and being able to see what they do. So how does this really work in effect what you do in your business? And how can I reduce this commissioning time? Well, today what we see out in the industry is most machine builders and people that build machines really have a similar process that's very serial. It starts up front with your sales group going out and gathering your requirements from the customers and bringing those back so we can build some concepts around those customers. Then we start up front with the mechanical design of how are we going to accomplish what the customer wants. And as we start building that mechanical design, we start passing it over to electrical design. And then usually at the very end is automation, where we give it to the automation group and say, okay, now go ahead and automate this entire machine that we've already built. Then once we've done all this, now what we do is we go ahead and we take it out to the manufacturing area, audit our customers for usually a factory acceptance test, where we take the machine we've actually built and we do real physical commissioning. That physical commissioning then will be able to then be turned on and turned into production. What we're trying to tell you, what we're trying to enable people today is with virtual commissioning is to enable not this serial process, but more of a parallel process. Whereas as soon as we get those requirements, we can now start taking those concepts and running through them very quickly to find the optimum solution for the solution we need. Also, while working at the automation and electrical design all at the same time, working on those serially so we can all talk together and quickly get together to the solution. And by doing this up front, what you can see is when we get out to the manufacturing area, what we're trying to say is at the end of the day, we realize many customers of your customers still might not be ready for 100% virtual factory acceptance test. But if I can reduce the time by that amount that starts showing on that white box in the real commissioning or the physical commissioning, I can now reduce the overall commissioning time out at the shop floor. Be out there, be more efficient, and get it done quicker. And really, what does that really mean to my business? And how can I really tie this to the bottom line is, this is really the standard we call the Six Sigma quality rule and the rules of tens. So every item I can fix up front, whether I catch it up front or whether I just get something up front done that I don't have to do later, for every stage of development, I save 10%. It's a factor of 10 down the road. So if I can find that up front when we're talking about that serial process, something that would, let's just say, cost me $1 today to fix, but if I got that all the way out to the shop floor, my customers' plant when I was doing factory acceptance testing, it would cost me $1,000 to fix it there. So this can quickly add up to a huge savings to your company to help you quickly find these problems and get them solved while it's easy to solve them. So also, virtual commissioning, what does it really do? Like I talked about before, not only does it lower the cost when you find these things up front, I can get through more iterations and do them faster. It really lowers the cost for real commissioning or what we call physical commissioning. And how is that? Because without virtual commissioning, I have these unexpected problems that may arrive. One is just the sheer time requirement that we were talking about. I'm out at my customers longer doing more physical commissioning, okay? How much time is this going to take? How long am I going to shut down their line to bring their machine on and integrate it into their existing system? The next one's personnel requirements. In today's world, too, of limited travel and social distancing, if I can take less people out to a plant, I can probably work more efficiently now, too, and keep people apart. So just the personnel requirements. The other one's the material requirements. If I'm solving all the problems up front and I'm not taking these machines out to the shop floor and finding out where the problems are, maybe one of the problems is we had some interference or some kind of other collisions or things we didn't detect up front, and now the material requirements are not only the parts are damaged out at the shop floor, so now I have to go back to the factory and have new parts made and shipped, so that all goes along too. And then the last one now is, even when international projects are involved, I mean, myself and Colin, we're based in the United States, so at present, we can't even travel to a lot of places in the world similar to you guys. So we're trying to eliminate the need to even travel as much as possible. So these costs can somewhat become incalculable due to these unknown factors. But when I use virtual commissioning, I get the best case. What I do is I eliminate my errors up front. Not only that, I can validate my sequence of operations up front with the actual code that's going to be installed on that machine. I can also set up, and Colin will talk about this is a big one too, and I haven't talked about it much now, is we can train the personnel that are going to use that machine well before it's built. And we can also, not only that, we can maybe get some early input from them on the interfaces that we're going to design and the screens and the layouts, how they're going to look. Maybe there's a better way that they would like to see it. And we can also use that digital twin for not only the validation of the machine, but then those customers will have their own digital twin of their machine, and they can use it for promotion, maybe at trade shows and other things. So this is a huge savings in there. So really, how does Siemens empower the machine builders today for virtual factory acceptance testing? Sorry, stumble there. Really, what it starts with NX. And NX is really the basis in our accelerator portfolio of building that digital twin, that mechanical model. And what NX is, it's a multidisciplinary platform that works not only in your mechanical design, but you can see down here we can also integrate electrical, process, and in our automation group. And today we're going to focus quite a bit on what we're calling mechatronic design, right? That's why we're here to talk about is how do I combine the mechanical design and the automation into one system, and this is where NX excels. And NX really does this through having the world's most productive modeling environments, embracing generative engineering to allow the computer to do the work for us, industrialized additive manufacturing, which is more than just building prototypes, but being able to actually build production parts with additive manufacturing technologies, electromechanical design, which is really at the heart of mechatronic design, where we combine electrical, mechanical, and in our case, automation. Collaborative design and management, really to now eliminate those parallel processes and get them serial so everyone can work collaboratively while managing all the data so everyone has the most up-to-date information at their fingertips. And finally, NX is really the gateway into integrated simulation and manufacturing. We're going to talk a lot about design today, but NX also, and Siemens as a group, we have a complete solution of simulation and manufacturing products to be able to do more simulation than we're showing today and also be able to build all the parts you need. So let's start with NX Mechatronics Concept Designer, and what does that really mean? And what you can see here is a copy of it on the screen. And what we have on the right-hand side is really a machine that's running, right? We got it all set up and we're running it. But if we look at the pop-out on the left-hand side, what we have there is what we're calling the Physics Navigator. And that's really how we connect the automation and the design together. You can see we have the folders here, right? We have just the regular basic physics of what rigid bodies do we have in here. We have a carousel, an axis, motors. Then what we need to do is we need to set up what we call the joints and constraints. How do these parts interact with their motion between each other? Then we have the materials, and then we have couplers, and then down near the end, when we start talking a little bit more, is we have the sensors and actuators built into this model so we can go connect them to our automation routines. And then we have down the roads, we have the actual signals coming in. So we connect those signals that's going to be coming from the PLC into this mechatronic system to drive it with. We can drive it originally with digital PLCs, and we can also drive it with physical PLCs. So And really that's what I was talking about here, because really the virtual environment is dependent on really everything, right? I come from a more mechanical background, and I'm really in this middle part here where we talk about the interaction between the mechanical and the automation system. When you think about being a machine builder and having factory acceptance tests, you also have to validate your PLC and HMI, and down the road, the interaction of a single machine into a complete factory and product cell. And from here, what I'm going to do is I'm going to go ahead and turn it over to Calm, who's going to take you through the rest of the presentation.
Thank you, Jay. So good morning, everyone, from my side. And just to pick up where Scott left off there, when we look at doing a virtual factory acceptance test, we have to look at, what is the use case that the machine builder needs to address? Is it just on the PLC or HMI interaction? Is it the mechanical interaction? Or is there, do you need to consider the simulation of the cell, the plant, or the whole line? And that's what really, when we look at the variety of SIEM tools from Siemens, this chart here shows you the different tools we have for the different use cases that you may need to simulate your machine in. And I'll go through each one of these in detail, but the focus, of course, for today is the Mechatronics Concept Designer. So all of these tools work on their own, standalone, or they can be combined to work together. And it's where we have our virtual PLC combined to work with the different modeling tools that we have you really can take the full advantage of the complete digital twin. So if we start looking at the what's important to think of when you create a digital twin for a machine, there are three main components. There's the automation model, there's the electrical behavior model for the drives, then there's the actual modeling tool that you can connect to. And when we look at those in detail from a Siemens standpoint, when we look at the automation model, our tool for our simulating our S7-1500 range of PLCs is Plc Sim Advanced. And this tool, released with version 14 of TI Portal, is a standalone tool which can simulate the complete program in the PLC, meaning safety, no protected blocks, web server. The complete program can be downloaded can be tested. And that's a big difference to a lot of, say, virtual PLCs on the market today. Critically, as well, it has the connection to the model via this API, so we can guarantee the high speed and, very important, synchronized communication between the modeling software and our virtual PLC. And in some cases as well, if need be, we can also do we can simulate multiple instances of the PLCs if you have more than one PLC controlling a system. Where you have coordinated motion, and you need to be able to simulate the behavior model of the drives involved, then we can use a tool called SIMIT. SIMIT can also be used to connect to a PLC to represent the process or the I/O. If I want to simulate, say, an I/O station or valves or motors, I can use SIMIT to simulate how those components will behave. But especially for the drive control, if you have coordinated motion on a machine, this tool will help you simulate how that give you much better, more accuracy on how the drive will behave. And then there's the different modeling tools then that we can connect to, be it Mechatronics Concept Designer or some of the other tools that we have to connect to. And if we begin going back to the different modeling tools, if we look at the SimCenter AMASIM, so this is a 1D modeling tool. Again, it's standalone, or it can work in conjunction with our virtual PLC or virtual drives. And the AMASIM tool, just to give you a quick overview, so it's 1D modeling tool, but it is multi-physics. So the thermal, the pneumatic, the electrical, the mechanical, all of the components on a machine, we can simulate how they will really behave. So this is really used for making sure you have the optimum size components on your machine, be it for the hydraulics or the motors or whatever it might be. And so we can also connect it to the machine once it's up and running to verify, have it connected to a benchmark. We can do virtual sensors and really see how is the machine performing how it's supposed to perform with a realistic simulation of the actual components used in the model. Then, of course, we have the Mechatronics Concept Designer, can work standalone or in conjunction with SIMIT and Plc Sim Advanced. And here is where we're going to get in, as Scott mentioned before. This is where we get into the validation, the definition of the kinematics on the machine. We bring the electrical and the mechanical and together much sooner. The mechatronic components that we're able to simulate can be saved in a library, so we can reuse them for much faster machine design going in the future. And of course, the sequencing, the traveling, the error handling, all of this we can validate early. But very important with the NXMCD tool is that the mechanical engineer can use this for an early design tool in addition to later on using it, combining it with the automation to do the virtual commissioning. Now, there are many applications where we have heavy-duty robots involved, like KUKA, FANUC, Staubli, ABB, and in this case here, we have our tool Process Simulate. So Process Simulate is not a CAD tool. It takes a CAD drawing as a starting point. We bring it into the CAD. We bring the CAD model into Process Simulate, where we can simulate how the robot will behave. Process Simulate is robot agnostic, so we can take part files in from many different vendors and then use those. We can teach the robot trajectories, check for collisions, for reachability, and of course, the key thing with Process Simulate is not only can we simulate how the robots will behave, but because it has the connection to our virtual PLC, just like all of our modeling tools, we can actually simulate the ancillary equipment around the robots. And this allows us to do a complete validation of the robot cell or the line. And at the highest level then we have plant simulation. Again, can work standalone or in conjunction with Plc Sim Advanced versus the virtual commissioning scenarios. And this we see heavily used in material handling applications, where it can be 1D or 3D models can be simulated to optimize material flow, machine layout, throughput capacity, working with AGVs, simulating how the AGVs work with warehouses. So in those use cases here, we can simulate how the plant will really behave. So for our purposes here today, though, we're going to focus in on the mechatronics concept designer, because this is one that we see the machine builders will use to help them optimize their machine, but the end user, your customer, will be requiring these digital twins or a better validation of, I want to see how this machine will work virtually before it's shipped to my site. So Plc Sim Advanced, starting there, that's what we mentioned before, the complete automation program can be tested. The API allows for this. This is the key portion with this, high-speed synchronized communication between the model and the PLC. Just like we mentioned before, we can stimulate the complete safety, the complete program. That's a key portion of this. And not only can we connect to the Siemens modeling software, but we can also connect via the API. Other third-party modeling softwares can also be connected by the API with Plc Sim Advanced. So a very powerful virtual PLC. And the key here again to differentiate this solution over, say, the competitors is this: Siemens has gone to the trouble of making sure that the communication, via this API, a high-speed synchronous communication, making sure that there's no data loss between what the PLC is running and communication between it and any of the modeling tools that we're using. So let's get into some of the use cases, how this would work. So we can bring in the model from a variety of different CAD tools. We can bring it into NX, which is the Siemens CAD package that Scott mentioned already. And once we have the CAD file, be a step file or JT format, once we bring that into NX, then we can apply Mechatronics Concept Designer is an option package on there, where we can then simulate, bring the 3D static model to life and apply the simulations for the machine. On the automation side, we have our TI portal. We use that to configure our PLCs, our HMIs and drives and so on, and safety, everything on the automation side. And the key here then is this Plc Sim Advanced for the virtual PLC. So we can do software in the loop, everything on one laptop, or can be split over multiple laptops if need be. And this, to go back to the image or the video that Scott showed earlier, on the left-hand side here we have a model that was brought in from SOLIDWORKS. We bring it into NX here. and then we can apply the kinematics to the grippers and extensions and so on. It can work standalone, or we can import in the I/O signals from a virtual PLC and use those signals to trigger the simulations that you see in the video. And just to show, this is not smoke and mirrors. This is a real machine. We have a digitalization showcase in Chicago for the pick and place, where you can see the digital twin side by side the real machine. Now, in many cases, we have customers who they want to connect to the real PLC, and we have what's known as, say, a hardware in the loop setup, and that's fine. We follow the same process. We bring the CAD file into NX. We apply Mechatronics Concept Designer to apply the kinematics, the motions, the simulations, and then on the automation side, if it's a real PLC, we make this connection to these PLCs by an OPC UA connectivity. So this works, it absolutely works fine, but for sure, this will not have the same level, the same speed, or the synchronization that we're using with our virtual PLC, Plc Sim Advanced. But it is possible, and I can show an example later connected to a third-party controller. So if we get into some of the use cases here, is how this is important for us. So if we look at, say, the collision detection. So in this example here, I'm starting my virtual PLC, Plc Sim Advanced, starting in the background, and then I have the code downloaded to it. The PLC is in run mode, and I connect the Mechatronics Concept Designer model to it. And you can see here there's a problem. The pole is in the wrong position, or I'm not telling the cylinder to extend to the right position. So what should I do? So there is a feature inside the Mechatronics Concept Designer where we can highlight the shapes involved with the collisions. And so with this feature enabled, we can see, in this case, we're trying to verify if the parts are mating correctly, but you can also use this to verify interference or collision as your machine is moving. And I know other CAD tools have an ability to do some level of simulation, but the key here is the motion that you're seeing is not being driven, well, we can drive it solely within the Mechatronics Concept Designer. In this use case, we've connected it to the virtual PLC, and it's the signals in the PLC that are driving the animation. That's a big difference. And of course, in this use case, we can just adjust the pole to make sure that the positioning is correct. This next use case, and I think a very important one, is just a use case of validating the sequence of operations. So I've enabled the second pick and place station here, and I've applied some physics on the different parts of the pick and place model. And this is where I'm going to bring in an example. I'm going to connect to the virtual PLC and bring in the PLC signals. And when I bring in the PLC signals, on the right-hand side of the dialog, you'll see the external signals there from the virtual PLC. The left-hand side are the MCD signals that we use to trigger the animations, or the simulations, and then I do an auto mapping. And that's key because then we are able to make sure that the tag names are the same between the virtual PLC and the model, and that drives an efficiency. Now here we can see we have a problem. I'm crashing into the pole, so my sequence is wrong. So what should I do? So in this use case, to correct this problem, I'm going to split the screen and open up my virtual PLC code, and I'm going to try to find the place in the logic that I'm driving this pick and place station. So in this case, I bring up a simple case statement, and this is the SCL programming within the TI portal, but this could be ladder logic program, function block diagram, it doesn't matter. Any of the ISE programming languages we can use. And when I run the model again and try to locate what is my problem here? So the pick and place station, it's moving back before it's moving up. So step 4 in my case statement where I'm telling it to move up, I just need to swap that. And the point here is not to explain how the code is working. It's really to illustrate I found an error in my code, whatever that might be. In this case, my case statements, my sequence were wrong. I make a correction to the sequence, so make sure I'm moving up before I move back. And then I download it to the virtual PLC and follow the exact same steps as if I was working with the real PLC. And then I monitor the code, go online, and then when I run the sequence again the second time, you'll see in this case, the sequence is now working correctly. So a simple use case you can verify from the machine builder, but of course on site, if that was not found, if you have a complicated machine kinematics, you want to make sure you're not crashing the machine before you show up at your customer site. The next use case is the error handling, and this is definitely one that the end user, the customer of this machine, will want a better validation for. How can I be sure your machine will recover if there's an error? In this use case here, we have a gripper open and a gripper close limit switch on this gripper. I'm going to introduce an error. I'm going to disable the gripper close limit switch. And when I do that, when I run the model the second time, as you can expect, the gripper comes down and it waits. But now what should happen? My virtual HMI should immediately come up with an alarm message telling the operator exactly what he needs to do to go fix this. Or if I have to find, if you notice on this machine, there are 2 or 3 other stations. What happens if one station fails? If there are other parts of the machine, how are they behaving? Will they go to a safe state? Will they keep on going? Will the turntable turn and try to shear off the head? So this is the thing as an automation engineer, having the visualization of a model that you can see how will it behave if you introduce faults is incredibly valuable, because you may be focused on one part of the machine, but now you can see how all of the components will work together. And this is the what-if scenarios that will drive you crazy on a commissioning application. Here's another use case where we see, and this is going on back to say on the design side for the mechanical engineer. In this case here, there's no connection to the virtual PLC at all. I have a sequencer at the bottom, a little Gantt chart, where I'm tying the sequences together. And this could be an early design part where the mechanical engineer wants to verify if the components, how he has designed this, if it's working correctly, so he can fill the box. So the parts come down through the chute, the box moves along, and this is, we would apply the physics as far as the weight of the box, the coefficient of friction on the conveyors, and then we can move it along. And you can see in the model here, there's a little pink kind of a tube there, and that's visualizing a virtual sensor. And we can see when the box crosses the virtual sensor, we can see then how the mechanics of the kinematics of the machine will work. So very helpful to troubleshoot the machine. And of course, this sequence editor will be replaced by the I/O signals coming from the virtual PLC or real PLC at a later time. Here's another early mock-up design, a filling application. So the filler will have to come down, fill the bottles, and then one of the really nice things, and you can see this is an early mock-up, so the mechanical engineer can verify, will this design work? But one of the really nice things within Mechatronics Concept Designer is a motion path like that. It will automatically generate the motion profile that an axis is moving. And so where do we use that? So this is a camming operation, where you define how one axis moves in relation to another. And we use this cam profile in our PLC, where we have a cam editor, where we define how one axis moves in relation to another. And this is where, this is a time-consuming process for the mechanical engineer and electrical engineer will work together to verify what should this motion profile look like. But in our case, we're able to easily find the file that was automatically generated with the Mechatronics Concept Designer, just import that into our TI Portal software, and we're done. So much, much faster for the engineering. And then we get into the use case of the virtual for training. So in this example here, we can see we have a simple demo machine with a gantry and a robot. But the key here is the HMI at the bottom. And this is a real machine we have here in the US for a demo center. And this is the complete HMI screen that we're simulating. So you can see when the robot starts to move, we can see the positioning points update on the screen. So if I'm an operator and I have to train, I have to learn how to use this machine, then I can work with this virtual HMI and go through all the screens, press all the buttons, crash the machine all day long in the virtual world, so I'm not doing it when the real machine is built. So this is, again, virtual factory acceptance tests. You can train an operator on how to use the machine, get familiar with the interface, or if the interface is too complicated, have operators, they can have influence. Well, it needs to be changed, it needs to be improved. And then most importantly then, if I'm the end user and I'm buying this machine, seeing this digital twin of the machine move beforehand, I now have a much better validation of how the machine will really work. And I can work with the machine builder to say, well, what happens if you hit the E-stop? What happens if you open the door? What happens if the sensor fails? All of those what-if scenarios can be discussed way before the machine is even built, never mind shipped and showing up on the customer's manufacturing facility. The training aspect, just to reiterate, just to put an extra focus on that, here not only can we do it all on a PC, completely software in the loop, but we can actually take the physical HMI and connect that with the push button station. We can connect that to a PC running the MCD and Plc Sim Advanced, so you can really replicate, if like, a training station that machine builders can use to help sell their machines. And I'm working with several machine builders in the US right now who are doing this. So they want to be able to offer this as a service to their customers. They want our training department to use this. And so it'll help them sell their machines, but it also gives their end customers, we've seen this actually from a large tire company, end customer, wanting a better training of their machines, better training of their operators, for their machines. And this is one way that we can do this. We talked before about connecting to third-party controllers. In this case here, we have the Mechatronics Concept Designer connected to the Rockwell PLC RS Logics. In this use case here, it is a hardware-in-the-loop setup, meaning that we did have a physical PLC from Rockwell connected to the MCD. We're doing this via OPC, so it is possible. So I just wanted to show, in this case, we're using a virtual Siemens HMI, but you could have a real Rockwell HMI, doesn't matter, controlling the operation connected to the real Rockwell PLC. So we just wanted to show you this because we recognize that, connecting the Mechatronics Concept Designer to third-party controllers is something maybe that you need to do. But of course, with the Siemens PLC, this is with the Plc Sim Advanced, the benefits there are the safety, as well as much faster, tighter synchronization with the API that's built in. And then for the success stories and references, so this was a company, Nextrom. This was a company that had thought that they had, over many, many years, producing a lot of the same machines, had optimized and had gotten their engineering time down to as best as they could possibly manage. But then working with the digital twin, being able to simulate everything, the processes, and working with the automation, they were able to reduce their time for development by up to 50%. And this is a video, we can send a link to this when we send these slides out, that shows the customers talking about, went from products in 12 months that took 18 to 24 months using traditional approaches. So dramatically in the reduction in the virtual commissioning and the commissioning time. Another company that this was an example, Tronrod Engineering, they're a high-speed packaging machine builder. And we see what they had said was very common. We see it with many other machine builders, reducing the design phase by up to about 10%. So making sure design options A versus design option B, making sure everything was working correctly. But then absolutely 20 to 25%, in some cases higher, reducing the actual commissioning time when the physical machine showed up on the shop floor. And we have a really nice video.
The commissioning phase for us is very, very nerve-wracking. We are producing prototypes, mostly, and bringing the machine to life is very nerve-wracking.
The machine is packaging different kind of pillow bags, like potato chips, or it could be salad bags, into cases, which is already erected and fed into the machine from external. And it does so in an unprecedented speed. Virtual commissioning for us means that we can actually test a lot of things in a virtual environment before we need to build the hardware. We realized virtual commissioning with the NX tool and the Mechatronics Concept Designer and the Plc Sim Advanced together with the TI port. main advantages we received on this machine with virtual commissioning is especially on the kinematics setup of this machine. Because of having two kinematic systems work in one shared space, we could test out the complete system in a virtual environment. And of course we had some virtual crashes, which saved us a lot of money.
When you do the design, production, assembly, then the software guy starts to program. In this case, he actually came out with the software, pushed the button, and it worked. No collisions.
By playing with a virtual model, you can learn a lot. And doing that, it's fun. Doing on the physical machine, that's not fun, that's scary.
When we use MCD to test out these things in a virtual environment in the office, of course we reduce the risk of damaging the machine. And of course every damage to the machine is quite devastating to the commissioning time. So that's a big risk saver.
Earlier I had a little board on each machine where they put a dot for each collision they ended up with. And this could be converted into expensive bottles of brandy for the team to share. Today they only drink water because all the collisions are done digitally, not on the real life.
Siemens, ingenuity for life.
So I think with that on the time, just to keep it tight today, I'm going to pass it back over to Jay. Hopefully that was some of the key highlights that we just wanted to show. And just to recap there, you know, the sequence of operations, the error handling, reducing your costs, reducing the risks for the commissioning, and then the training options that are available that help both the machine builder and your end customer who want that as well. So I'll pass it back to you, Jay.